I would like to start. So, welcome everybody. We are here we are very fortunate to have the presence of Jean Rintoul. She's a PhD from Imperial College in, I guess, neurotechnology. You can correct me, Jean. And she's going to present now her work in open source tomography with electrical impedance. And with that, I give you the floor, Jean. Thank you so much for coming.
Thank you so much. Let me just... Electrical impedance tomography is a project I started 8 years ago. Originally thought it would be wonderful if medical imaging was more accessible. Since 2/3 of the world has no access to medical imaging, if we could make it more accessible, would have different outcomes for health. So MRI costs a few $1 million, CT scans, ionizing radiation, and as well as a few $1 million. And ultrasound is good, still a bit expensive, but it only gives one kind of information. So why be motivated to make it more accessible? Computers started off being very large, the size of a room, and nobody could experiment with them. It's actually when they became smaller and individuals and small groups could afford them that we really had a renaissance in innovation. Obviously now we have the smartphone, which is the result of all of that excitement and efforts by so many millions of people. If we could do the same thing with medical imaging, here's an MRI, which is the size of a room, to make it smaller and more accessible, imagine where we could get to. This is an image of the tricorder in Star Trek, just as a sort of idea of what would be awesome. So I'm going to talk about a specific imaging technique, electrical impedance tomography. It was built in the 1980s or discovered in the 1980s. It's where you send through small currents and you measure their amplitude or voltage on the other side, and use an algorithm to reconstruct an image of how that impedance measurement changes as you put that current through different angles around the body. It's historically been used for lung imaging, but you get this kind of blurry image here on the right. Later, David Holder and Kirill Aristovich at UCL pioneered fast neural EIT, which seemed like a really promising technique for brain monitoring, and I became very excited by it then. So how does it work? Well, so different tissues have different resistances, and current will bend based on the its least path of resistance. So if you can imagine just cells up here on the upper left, current at one frequency will bend around the cells because of that capacitive higher impedance cell membrane, and at a different frequency it may go straight through. So this effect means that we can measure these different impedances when we send current through from different angles. And here we have what you typically call a phantom, which is basically just a bowl of water with some vegetables in it, and you can reconstruct this kind of rough image here. So I went off and I prototyped an electrical impedance tomography system, and here it is. And you can see that it can reconstruct an image. Those are two cups in a phantom. Here you can also see an anti-clockwise rotation of that cup, and the reconstruction able to localize where that cup is. The way that it works is similar to a CT scan. So what happens is that when you send current through and measure it at the other side, you get this single line. And if you get enough of these lines at different angles, here you can see that the various electrodes and the combinations, you can then do something called the radon transform, is the simplest algorithm or back projection to reconstruct that image. So in the case of electrical impedance tomography, because you need a balancing of current and voltage differential voltage measurements, you would send through a current through one set of electrodes, and then you'll measure voltage and rotate that around different electrodes. So I ended up making Spectra, the name of this EIT system, open source on GitHub. It's got various tutorials, and this is the board, which I designed quite some time ago now, and I'll sort of talk about what I've been doing in the meantime shortly. Bioimpedance spectroscopy connectors, and it's based around this precision impedance measuring chip. So the architecture design is basically power management, analog signal processing with multiplexers, which are used to rotate around the choice of electrodes. As I was mentioning before, you have to do a whole lot of measurements to reconstruct an image, and that all goes out to the phantom tank where you can do the reconstruction. It's powered by this Python dashboard, which is leveraging PyEIT, which is another project that does specific EIT reconstruction algorithms. There's a few, and they go far beyond back projection. And the basic device and firmware is all open source. So typically, this sort of thing has been used for lung imaging. And you'll notice it's really low resolution. But at that point, I would go back to the first MRI scan, which was, I think, July 3rd, 1977. And this is an MRI scan of someone's lungs. It looks very low resolution. It's not very impressive. This is now, actually, this was a few years ago. This is an MRI scan of my head at UCSF. And you can see that we've come a long way with MRI. It's an absolutely fantastic tool. We get much higher resolution. So the question is, how would we get higher resolution using an impedance measurement technique? We could increase the number of electrodes, have better algorithms. We could send through more current. There's a lot of different options. So the other thing that I think electrical impedance is really good at is impedance spectroscopy, which is where you send through different excitation frequencies and you make a spectrum. So here, I measured the spectrums in this water bath of an apple and a sweet potato over a number of days, and you can see that the spectrum over each day is actually quite repeatable, which meant that some basic k-means clustering over here on different days, you can actually see which one is the apple and which one is the sweet potato. And I thought this was really, really interesting. There's lots of studies showing it can do material differentiation. If you applied that to breast cancer or glioblastoma, I think you've really got something great. So to actually distribute this to others, we sold a pre-tested and manufactured device that works out of the box, which saves researchers time to get up and running. So again, this was quite a while ago that this project was initially developed. It was presented at a number of hacker conferences at the time. Over this period, I sort of realized my interest in medical imaging was non-trivial. And there was a crowdfunding campaign which succeeded and ended up delivering this to over 100 backers. And I got at the end of this, I got a small amount of funding from the Gordon and Betty Moore Foundation, Moore of Moore's Law. And then I made it into a PhD program at Imperial College, which I've been doing almost since then, 2020 to 2025. But now I'm getting back into how do we make medical imaging more accessible? And I was developing a new form of non-invasive neurotechnology during that time. So some highlight projects that people did. I was also selling this Spectra kit at the beginning of my PhD and started doing that again. And I thought it would be great to sort of say what some people did with it, because I think that's really interesting. It's not only interesting that some people did some things, it's interesting to see that people came up with ideas that I never would have, and a whole variety of them. And I think that's the beauty of it. So the classic is lung perfusion monitoring for pulmonary embolism. Mayo Clinic was interested in spectra for intracranial pressure monitoring, which incidentally I think is a really great application. Another really interesting startup application was, so in the IVF industry, obviously there's a lot of money, but also a lot of regulation for human IVF. However, bovine IVF is very popular, and this is how we breed cows. And what we need to do is assess the quality of embryos. So they had microfluidic chambers, and they had little small arrays for the EIT and bioimpedance spectroscopy analysis of embryos. There was a dentist who had a dream of replacing X-ray machines for cavity detection with EIT, and I thought that was very interesting. From the open angle, the founder of the RepRap project, which is an open source initiative started in 2006 to create a low-cost self-replicating 3D printer capable of printing most of its own plastic components. And it led to this 3D printing revolution, really. It was led by Dr. Adrian Bauer, and he was interested in it for this kind of follow-on interesting project of an electric 3D printer where you use electric current to set this liquid plastic monomer polymerase, and that would use EIT in it, but it had a whole lot of other moving parts as well, and it was like, oh, what an interesting idea of combining those things. A gastrointestinal doctor in New Zealand, prosthetics lab wanting better gestural control, nerve fascicle imaging, sleep apnea analysis of the throat, body fat and muscle analysis tool. So all of those impedance scales that differentiate between fat and muscle are a popular kind of application for this sort of thing. Deep vein thrombosis monitoring, vaginal mucus for fertility prediction, advanced fistula creation for dialysis. And NASA bought one, but I don't know what they did with it, but I thought it was kind of cool. So all in all, I think this project encouraged innovation and acceleration of health technologies in general, but there are problems with EIT in general, and I'm sort of just going to, I don't want to be a downer, but I'm going to go there. Electrical impedance tomography has issues with contact impedance. So if you have a ring of electrodes around your wrist, say, for gestural, doing gestural recognition, if the electrode skin interface changes, that can cause problems with the image reconstruction. And this is a big problem. So this is why EIT works really quite well in a tank, but when you move it to the body, there's a lot more problems with, and this is all to do with this contact impedance, which you can try to control for by keeping the surface area of the different electrodes the same, but it's quite possible with movement and various compensation techniques that this could be a problem. You can add more electrodes, so you can implement an averaging technique, yes, but it remains a problem. There are also problems in terms of image reconstruction. The algorithm that I described, the most simple back projection, assumes current travels in straight lines. This is true for X-rays. X-rays travel in straight lines, but current certainly does not travel in straight lines, nor is it purely resistive. It's actually got capacitive components as well. The field lines don't even travel in 2 dimensions, which is also an assumption of the algorithm. They travel in 3 dimensions, which is very hard to capture with only 2 dimensions of electrodes. And this last point, I think, is both the beauty of this technique and its downfall, is that the dielectric impedance of body parts that were wildly inhomogeneous and anisotropic. So this means that from different angles, the impedance will be different. So more electrodes will only get you so far to enhance your algorithm reconstruction, and those more electrodes could introduce further contact impedance issues as well. So with that, I would want to focus on bioimpedance spectroscopy because this is awesome and a repeatable material differentiation. However, I don't think bioimpedance spectroscopy is that appealing to clinicians because it just doesn't produce a beautiful image. EIT or impedance measurements are great for portable or mass manufacturing. So they do have a lot of potential if you need a field monitoring system or a bedside non-invasive system. But I don't think it's ever going to have high spatial resolution. But what it can do is have high information density using spectroscopy. So this won't be pretty, but it's a perfect application of machine learning. So this would be the direction to go in. So Spectra's frame rate was also limited. This is just Spectra, not EIT in general, because it used an onboard FFT calculation based on the microprocessor I chose, which was it was accurate, but it was not fast enough, in my opinion, for the large numbers of electrode combinations you need to do, say, 32 electrode image reconstruction. You can get over this by doing, and the ideal would be to do much higher frame rate, multi-frequency. So you're getting, say, impedance spectroscopy information with spatial information at the same time. So to do that, realistically, with a good time resolution, say milliseconds, you would need FPGAs, and this also ups the development and parts costs. So now we're looking at a slightly more expensive kind of system. And it got me to thinking about electrical only based techniques in general. You see, at say 2 kilohertz or 15 kilohertz, your wavelength's about 200 kilometers, which is outside of the length scales of the human body. What I think we should do is go with something where the length scales are in the human body range, so that then you can do things like beamforming or phased arrays to do high spatial resolution focusing. And ultrasound is the way to do that. Ultrasound has a wavelength of 3 millimeters, 0.3 millimeters, dependent on what frequency you're at. And I've got an ultrasound field on the right there. So you can use short wavelengths to gain focality. However, ultrasound typically doesn't give you impedance data to date, which is why I thought, during my PhD, we should better understand the relationship between acoustics and electric fields in conductive materials, of course, like the body and the brain. Because I think this is the key to interacting electrically with the body, seeing things with the spatial resolution of ultrasound. So what is the acousto-electric effect? It was actually discovered back in 1946, looking at sonar in the Navy by Fox, Hertzfeld, and Rock. So what they found was that when you have an acoustic wave, it compresses and rarefacts that the ionic solution, say a chunk of meat, brain, or another body part, or even just salt water. So when you pull the ions apart and push them together, you change its conductivity or resistance, if you're in scalar terms. And then if you remember Ohm's law, V equals IR. So now if you have an oscillating resistance and you apply a constant current, you get a changing voltage. But here, this changing voltage is now having the spatial resolution of ultrasound. So this is a great way to do targeted electrical measurements. So during my PhD, I looked into what the acousto-electric effect really is, and found it was actually a frequency mixing effect. What's a frequency mixing effect? Well, basically, when you multiply an electric signal by an acoustic signal, they create a sum and difference frequency. This is really neat because you know exactly where to look. So if you have a sum and difference frequency that they look like this together, you can look at 492 kilohertz and 508 kilohertz and measure precisely where this acousto-electric effect is happening. It was statistically significant. There's a paper. And so what is heterodyning, just to sort of go back to why this would be sort of useful, is actually so it's frequency mixing, and it's been used everywhere. It's used in AM radio, in semiconductors, in diodes, lots of engineering innovations. So in radio, what we have is a low frequency signal in the form of a voice, say, and a high frequency radio wave. And they mix together or multiply together. And then that low frequency sound signal will frequency shift up to the sum and difference frequency around the radio frequency carrier wave, where you can detect it. And this is a great way to isolate information. And then the recovery process is the same. It's also another multiplication. But previously, this has been done electrically only. But here, we're talking about it being done between an acoustic and electric field. And that allows us to use the various aspects of both of these different types of fields together. So there's prior work in something called ultrasound current source density imaging, which has been applied to cardiac monitoring. So here, they have an ultrasound, and here is a heart, and they can measure these electrical changes with an externally placed electrode, which I think is very interesting. And this is using the acousto-electric effect. So what we're showing is that you can measure electrical information in the body using the focality of the acoustic field. So to overcome focality limitations in EIT, I think the next step really is to use a cross-modality technique, which utilizes the shorter wavelengths of ultrasound while still detecting and affecting electric fields, as these show great contrast in the body. So electric fields are fantastic for this dielectric impedance variation, but the way that they travel through the body is horrific from an algorithm standpoint. It's just impossible. So if we have a look at the techniques, we've got electrical impedance tomography over here, current injection electrodes, current lines, all bending, and our measurements, and that's an all electrical technique. There's another technique called MREIT. I think Professor Rintoul said earlier is very good at that, but this one needs an MRI, so this is a slightly more expensive technique, but it's quite effective. Then there's Lorentz force electrical impedance tomography, which is where you use a static magnetic field. So people are starting to mix these electric fields and acoustic fields together. And of course, acousto-electric imaging here, which doesn't need a huge amount of equipment comparatively, but does have this ability to have the spatial resolution of ultrasound and acquire electrical measurements. So I think there's a lot of potential there. So what's next for this? How can a version 2 emerge? Well, yes, this entire effort has actually been mostly self-funded, apart from customer purchases, thank you. And of course, that wonderful 50K grant from the Gordon and Betty Moore Foundation, which was about 6 years ago. And there was also a gift from NeurotechX, which I'm very grateful for. It's not running on a multi-million-dollar grant as yet, and it doesn't have a larger number of people paid continuously to develop it. So basically, fundraising is on the table. So we're applying for grants and seeking scientific collaborators which fit with specific grant calls where Mind's Eye creates novel hardware and collaborating labs perform application-based experiments, creating high-impact publications in medicine and neuroscience. If you know people who are interested, please get in contact. Altogether, and this is 8 years later, I will say one thing, that I still believe in the basic goal of this project, that advancing medical imaging is still a very important problem for humanity. And overall, we don't put as much resources into what seems like such an important thing to do, where we can make tangible technological leaps forward on relatively sane budgets as well. I really think this is a really high potential area. So it'll be interesting to see what happens in future. So I'd just like to say thank you to everybody and happy to answer any questions. You can visit the project here and there's a website over here. So thank you very much, everybody.